Reality itself operates by a set of rules that seem to defy all common sense. We are entering the quantum realm, a place where particles exist in multiple places at once, where simply looking at something can change its behavior, and where the solid logic of cause and effect we rely on simply falls apart. This journey will uncover 20 astonishing ways the quantum world shatters classical logic. And by the end, you will gain a completely new perspective on the very nature of existence itself. We will unravel mysteries that baffled even Einstein, from a cat that is somehow both alive and dead to particles that communicate instantaneously across the universe. What does it truly mean for our reality if the fundamental building blocks of everything operate on pure paradox? The very first crack in the classical view of reality appeared with a simple yet deeply confusing question. What is light made of? For centuries, scientists argued over whether it was a wave like ripples on a pond or a stream of tiny particles. The quantum answer, it turns out, is both and neither. This is wave-particle duality, the first and perhaps most fundamental way the quantum world defies all logic. A single photon of light, or even an electron, will behave as a perfect particle if you set up an experiment to catch a particle. It will hit a detector like a tiny bullet at a single point. But if you change the experiment to look for a wave, that same entity will suddenly act like a wave, spreading out and exhibiting interference. This bizarre behavior was cemented by the famous double-slit experiment. When particles are fired one by one at a barrier with two slits, you would expect to see two clusters of impacts on the back wall, just like bullets. But that is not what happens. Instead, an interference pattern emerges, a series of light and dark bands that can only be created by waves overlapping and canceling each other out. It is as if each individual particle is going through both slits at once and interfering with itself. This forces us to abandon the classical idea that an object has a single, definite identity. A quantum entity does not choose to be a wave or a particle until the very moment it is measured. Until then, it exists in a blurred state of potential, a reality that is not fixed but probabilistic. The great physicist Niels Bohr called this complementarity, insisting that these two seemingly contradictory natures are not a problem to be solved, but two complementary truths necessary for a complete description of reality. So how can one thing be two things at once? This paradox leads us directly to an even stranger quantum behavior, one that places a cat in a box with a fate worse than death. This very idea of a blurred reality led Erwin Schrödinger to devise a thought experiment so unsettling it has become legendary. He imagined placing a cat inside a sealed box with a vial of poison, a radioactive atom, and a Geiger counter. The setup is designed so that if the radioactive atom decays, the Geiger counter triggers a mechanism that shatters the poison vial, killing the cat. But here is the quantum twist. According to the rules of the quantum world, that single radioactive atom exists in a superposition. It is both decayed and not decayed at the same time. And because the fate of the cat is tied directly to the state of that atom, the cat itself must also be in a superposition. It is, in a sense that defies all reason, both completely alive and completely dead simultaneously. This is the principle of quantum superposition, the second great defiance of classical logic. We are forced to accept that a system does not have to choose a single state. It can exist in a blend of all possible states at once. This is not just a philosophical puzzle. It is a fundamental property of the universe that has been confirmed repeatedly in laboratories. Scientists can trap a single particle, like an electron or a photon, and demonstrate that it genuinely occupies multiple positions or energy levels at the same time. It is only when we finally open the box and look, when we make a measurement, that this fuzzy cloud of possibilities is forced to pick a single, definite outcome. The cat is either alive or dead. The atom has either decayed or it has not. This instant transition from many possibilities to one reality is called the collapse of the wave function. But why does observation cause this collapse? What is so special about the act of looking that forces nature to make up its mind? This question pulls us toward the next great quantum mystery, one that places the observer at the very heart of reality itself. This act of looking, of taking a measurement, is the very thing that shatters the superposition. It forces the universe to make a choice, and this is the third great defiance of classical logic, known as the measurement problem. In our everyday world, measurement is a passive act. You use a ruler to reveal the length of a table, but the table had that length all along. Your observation did not change it. The quantum world operates by a completely different, and frankly bizarre, set of rules. There, the property you are trying to measure does not even exist in a definite state until the moment you measure it. Your act of observation is what forces a single reality to emerge from the cloud of possibilities. It collapses the wave function. The dominant explanation for this for decades has been the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. It states, quite radically, that reality is not objectively real until it is observed. The moon is not there when nobody is looking. This interpretation suggests that consciousness itself, or at the very least a conscious interaction, plays a fundamental role in shaping existence. It places the observer at the very center of the universe, a thought that is both empowering and deeply unsettling. But not all physicists are comfortable with giving consciousness such a profound power. This has led to other wild interpretations like the many worlds theory. This idea suggests that the wave function never actually collapses. Instead, at the moment of measurement, the entire universe splits. In one branch, you open the box and find a live cat. In another, completely separate branch, a different version of you finds a dead one. Every possible outcome happens just in its own parallel reality. This avoids the strange collapse, but introduces an infinite and mind-bogglingly complex multiverse. So, does our looking create reality? Or do we simply choose which branch of reality to experience? The measurement problem shows us that quantum mechanics is not just a theory about tiny particles. It is a theory about information, knowledge, and the fundamental relationship between the observer and the observed. It blurs the line between the subject doing the seeing and the object being seen, suggesting they are inextricably linked. And this intimate link between observation and reality leads us directly to a related principle that limits what we can ever know, a fundamental uncertainty woven into the fabric of the cosmos. This fundamental uncertainty is not a flaw in our instruments, but a law of nature itself. This is Heisenberg's uncertainty principle, the fourth way the quantum world defies all classical logic. It states, with unshakable certainty, that we can never simultaneously know both the exact position and the exact momentum of a particle. The more precisely you pin down where a particle is, the less you can possibly know about where it is going and how fast. It is not that our tools are too clumsy. It is that the particle does not possess both a definite position and a definite momentum at the same time. This is a direct consequence of its wave-like nature. A wave, by its very definition, is spread out. A perfectly defined position would require an infinitely sharp spike, which is not a wave at all. Conversely, a particle with a perfectly defined momentum would be a perfect wave with a single wavelength, stretching out across the entire universe, meaning it has no specific location. This principle shatters the classical dream of a perfectly predictable universe. In Isaac Newton's clockwork cosmos, if you knew the position and velocity of every particle, you could calculate the entire future and past of everything. The universe was deterministic. Heisenberg's principle proves that this is an impossible fantasy at the quantum level. The universe is not a clock. It is fundamentally fuzzy, built on a bedrock of probability. This inherent uncertainty forces us to abandon the very idea of a particle having a neat, well-defined path through space. There is no tiny planet following a perfect orbit around a nucleus. Instead, there is a cloud of probability, a haze of potential locations where the electron might be found. The electron exists in a sort of blurred reality, a superposition of all its possible paths until the moment it is observed. So if particles are these fuzzy clouds of probability, without definite paths or certain properties, how can they ever interact with each other in any reliable way to build the stable world we see around us? This question leads to one of the most bizarre and profound phenomena in all of physics. This inherent fuzziness of a single particle is strange enough, but the quantum world has an even more baffling trick up its sleeve, one that connects particles in a way that seems to defy the very fabric of space and time. This is quantum entanglement, the fifth great defiance of classical logic. Imagine creating two particles in such a way that their properties are intimately linked, like two coins spinning in perfect unison. Now, separate them by any distance you can imagine, send one to the opposite side of the galaxy. According to quantum mechanics, these particles remain a single, connected system. If you measure one particle and find it spinning in a certain direction, you instantly know its partner is spinning in the opposite direction, no matter how far apart they are. This instantaneous connection is what so troubled Albert Einstein. He famously derided it as spooky action at a distance, because it appears to violate a core tenet of his theory of relativity, which states that no information or influence can travel faster than the speed of light. How could one particle possibly know what happened to its partner without some signal flying between them faster than light? Einstein believed there must be some hidden variables, some predetermined classical plan that we just could not see, which would explain the correlation without any spooky action. For decades, this was a philosophical debate. Then, in the 1980s, a physicist named Alain Aspect performed a series of brilliant experiments. His results were clear and shocking. There were no hidden variables. The particles were genuinely connected in a way that transcended space. Measuring one did instantly affect the state of the other, confirming that spooky action was real. This phenomenon is not just a laboratory curiosity. It is the foundation for emerging technologies like quantum cryptography, which allows for perfectly secure communication, and quantum teleportation, which can transfer the quantum state of a particle from one location to another without it ever physically traveling the space between. Entanglement forces us to confront a startling possibility that the universe may be fundamentally non-local. The properties of objects may not be confined to a specific point in space, but could be shared across vast, seemingly separate regions. This suggests a deep and invisible interconnectedness to all things, a cosmic web that operates beneath the surface of our classical reality. If two particles can be instantaneously linked across a galaxy, what does that say about the true nature of separation? It challenges the very idea that objects are truly independent, pointing toward a reality where everything is part of a single, unbroken whole. This instantaneous link between entangled particles forces us to confront a truth even more radical than spooky action. We must accept the reality of quantum non-locality, the sixth great defiance of classical logic. This is the astonishing idea that objects can influence one another directly, regardless of the distance separating them, violating our deepest intuitions about space and causality. In a local universe, as Einstein insisted, any influence must travel through the space between points, limited by the cosmic speed limit of light. But non-locality shatters that view, suggesting a connection that operates outside of space itself. The final proof came from a physicist named John Bell. He devised a mathematical theorem, a test that could definitively settle the debate between Einstein's hidden variables and true quantum weirdness. If the universe were local and realistic, as Einstein hoped, Bell's inequality would hold true. The correlations between entangled particles would have a strict upper limit. But when scientists like Elaine Aspect performed the experiment, the results were unequivocal. The quantum particles violated Bell's inequality by a huge margin. There was no hidden plan, no local explanation. The universe was fundamentally non-local. Now, this does not mean we can send a message faster than light. The outcome of each measurement is always random. You cannot force your particle to take on a specific spin to send a coded signal. It is only when you compare your results with someone holding the other particle, using a normal light-speed communication channel, that you see the miraculous, instant correlation. No usable information is transmitted faster than light, but the connection itself is undeniably instantaneous. This presents a profound philosophical dilemma. It suggests that the universe is not made of separate, independent parts. Instead, it seems to be a deeply interconnected, holistic entity. The properties of one particle are not its own alone. They are shared properties of a system that transcends physical separation. This challenges the very foundation of reductionism, the idea that to understand the whole, you simply break it down into its constituent pieces. At the quantum level, the pieces are not truly separate. They are woven together into a single, unbroken tapestry. So how do we reconcile this with Einstein's theory of relativity, which so perfectly describes a local universe where space and time are the ultimate stage? This creates a deep and unresolved tension at the heart of modern physics. One theory tells us that space and time are the immutable framework of reality, while the other hints that they might be emergent illusions, a surface-level appearance hiding a far stranger, interconnected whole beneath. But this interconnected web of reality is not the only rule the quantum world breaks. It also shatters our most fundamental understanding of energy and motion. A particle confined within a box, according to classical physics, simply cannot escape if it lacks the energy to climb the walls. It is trapped forever. Yet in the quantum realm, particles routinely perform this impossible feat. They vanish from inside a sealed container and spontaneously reappear on the outside, as if they simply walked through the wall. This is quantum tunneling, the seventh great defiance of classical logic. Think of it like a ball rolling toward a hill. If the ball does not have enough energy to reach the top, it will always roll back down. It is an unbreakable rule of conservation of energy. But in the quantum world, that same ball, representing a particle like an electron, has a small but real chance to simply appear on the other side of the hill without ever having gone over the top. It does not climb the barrier, it tunnels through it. How is this possible? The answer lies once again in the wave-like nature of quantum objects. A particle is not a tiny, well-defined marble. It is a cloud of probability, described by its wave function. This wave function does not abruptly stop at an energy barrier. Instead, it decays exponentially inside the barrier, like a fading echo. If the barrier is thin enough, the wave function does not fade to zero. A tiny yet finite part of it extends out the other side. This means there is a small probability that the particle will be found there. It is not a guarantee, but a roll of the dice on an unimaginably small scale. This is not a theoretical curiosity. Quantum tunneling is the very reason our sun shines. At the core of a star, protons need to collide and fuse to release energy. But they are all positively charged, and they repel each other fiercely. The energy required to overcome this repulsion is far greater than the energy the protons possess from the heat of the sun's core. Classically, fusion should be impossible in a star like ours. But thanks to quantum tunneling, there is that tiny, miraculous probability that a proton will tunnel through the energy barrier of repulsion and get close enough to another to fuse. This happens constantly, and it is why stars exist at all. This same effect is the engine behind many modern technologies, from the transistors in your computer to the flash memory in your phone and the sharp tips of scanning tunneling microscopes that allow us to see individual atoms. Quantum tunneling rewrites the meaning of impossible. It shows us that in the quantum world there are no absolutes, only probabilities. No wall is ever truly solid, and no barrier is ever completely insurmountable. There is always a chance, however faint, for the seemingly impossible to occur. And if particles can borrow a sliver of probability to tunnel through solid walls, what does that imply about the nature of empty space itself? Is a vacuum ever truly empty, or does it seethe with a hidden, restless energy? Even the very concept of nothingness is a lie in the quantum world. This is the eighth great defiance of classical logic, the reality of zero-point energy. Classical thermodynamics tells us that as a system cools, the motion of its particles slows down. At the theoretical temperature of absolute zero, all motion should cease entirely, achieving a state of perfect frozen stillness. The quantum realm, however, utterly rejects this idea. Even at absolute zero, a quantum system is never truly still. It retains a residual, eternal vibration, a hum of energy that can never be switched off. This is zero-point energy, and it is a direct and unavoidable consequence of the uncertainty principle we just encountered. Remember, a particle can never have both a definite position and a definite momentum of zero. To be completely at rest would require it to have exactly zero momentum and be in an exact location, which is strictly forbidden by the laws of quantum mechanics. The particle is therefore compelled to jitter and vibrate, forever trapped in a tiny, irreducible dance. This is not just a theoretical idea. We can observe its effects in the laboratory. The most famous demonstration is the Casimir effect. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, they will be gently pulled toward each other. Why? Because the empty space between the plates is not actually empty. It is seething with a sea of transient quantum fluctuations, often described as virtual particles popping in and out of existence. The plates act like a filter, restricting the kinds of fluctuations that can appear in the narrow gap between them. Outside the plates, a wider variety of these fluctuations can occur, and this imbalance in pressure literally pushes the plates together. It is a measurable force generated by the restless energy of nothingness itself. This reveals a truth far stranger than any science fiction. There is no such thing as a true void. What we call empty space is, in fact, a vibrant, bubbling foam of potentiality, a quantum field alive with fleeting energy borrowings and repayments. This zero-point energy is woven into the fabric of the universe, a background hum that influences everything from the stability of atoms to the very expansion of the cosmos. It shows us that stillness and nothingness are classical illusions. Existence is fundamentally restless, and even in its deepest freeze, the universe refuses to be silent. But what are these virtual particles that give the vacuum its texture? And how can something come from nothing, even for a moment? This restless energy of the void is not just a vague hum. It is a seething sea of spontaneous creation. The ninth great defiance of classical logic is the reality of virtual particles. These are not particles in the traditional sense you might imagine. Instead, think of them as fleeting ripples in the quantum fields that make up our universe. They pop into existence from seemingly nothing, borrowing a tiny amount of energy from the vacuum itself, and then they vanish back into nothingness almost instantly. This entire process happens far too quickly for us to ever see them directly. They are called virtual precisely because they are these temporary, unobservable fluctuations. Yet their effects are undeniably real. This bizarre behavior is made possible by the uncertainty principle, but applied to energy and time. Just as we cannot know a particle's position and momentum with perfect certainty, we also cannot know its energy at a precise moment. For an incredibly brief window, energy conservation can be violated. The universe allows for a loan of energy as long as it is paid back almost immediately. This is how a particle and its antiparticle partner can spontaneously appear, exist for a vanishingly short duration, and then annihilate each other, returning the energy they borrowed. This is not some abstract theory. Virtual particles are the workhorses of the quantum world, responsible for mediating the fundamental forces. For example, the electromagnetic force between two electrons is not some magical action at a distance. It is actually carried by a constant exchange of virtual photons, shuttling back and forth between them. This is how forces are transmitted at the quantum level, through a frenetic game of subatomic catch using particles that barely exist. Their reality is confirmed by measurable effects, like the Lamb shift. This is a tiny change in the energy levels of an electron in a hydrogen atom, a shift caused solely by the electron interacting with the virtual particles popping in and out of the vacuum around it. Even more profound is their role in Hawking radiation. At the edge of a black hole, virtual particle pairs appear as always. Normally, they annihilate. But if one particle falls past the event horizon while its partner escapes, the black hole effectively pays the energy debt for the escaped particle. To an outside observer, it looks like the black hole is slowly emitting radiation and losing mass, eventually evaporating over eons. This means the vacuum is not an empty, static stage. It is a dynamic, bubbling foam, a constant dance of creation and annihilation happening everywhere all the time, even in the seemingly dead space between stars. It reveals that existence itself is not permanent, but fleeting and probabilistic. If even empty space is this alive with activity, how can our theories of gravity, which describe the smooth curvature of space-time, possibly account for this chaotic, granular quantum foam? This is the greatest unsolved problem in all of physics. This relentless dance of virtual particles, this quantum foam, presents physics with its greatest and most stubborn challenge. We now face the 10th great defiance of classical logic, the monumental problem of quantum gravity. For nearly a century, we have possessed two incredibly successful but utterly incompatible descriptions of reality. On one hand, quantum mechanics governs the bizarre world of the very small with stunning accuracy. On the other, Einstein's general relativity masterfully describes the force of gravity and the large-scale structure of the cosmos, picturing space-time as a smooth, continuous fabric that warps and curves. The conflict arises when we try to combine them. General relativity treats gravity as the geometry of this smooth space-time stage, while quantum mechanics insists that everything, including the actors on that stage, must be granular and quantized. When we push our theories to the most extreme environments, like the center of a black hole or the very first moment of the Big Bang, where both immense gravity and tiny quantum scales coexist, the mathematics simply explodes. The equations of general relativity break down, producing nonsensical answers like infinite densities, a sure sign that our theory is incomplete. To resolve this, physicists believe we need a theory of quantum gravity, a framework where space-time itself is not smooth, but made of tiny, discrete grains or loops at the smallest possible scale, the Planck length. This is a distance so vanishingly small that 1,000,000 trillion of them would fit across a single proton. At this scale, the very ideas of here and there, before and after, might cease to have any meaning. The smooth continuum of space and time we experience would then be an emergent illusion. Much like a movie appears continuous, though it is really a series of still frames. Ambitious attempts like string theory propose that the fundamental entities are not point-like particles, but incredibly tiny, vibrating strings, whose different vibrations give rise to all the particles and forces. Loop quantum gravity, another approach, suggests space is woven from a network of finite loops, a spin foam of evolving connections. The profound defiance here is that these theories force us to abandon the last vestige of classical intuition, the stage of space and time itself. They imply that reality, at its core, might be built from pure information or abstract mathematical relationships, not things residing in space and time. The most humbling part is that, so far, we lack any experimental evidence to guide us. The energy required to probe these Planck scales is far beyond anything our particle colliders can ever achieve. This stalemate tells us something deep. Our understanding of the universe is fundamentally incomplete. We are missing a crucial piece of the puzzle, a new principle that will forever change our conception of reality. And this leads to a truly radical question. If the act of observation is so crucial to defining reality in the quantum realm, could the mind itself, consciousness, be that missing piece? Could the observer be more than just a witness, but an actual participant in the construction of space and time? The very idea that consciousness could play a role in shaping reality leads to a breathtaking, if controversial, possibility. What if the mind itself is a quantum phenomenon? This is the 11th great defiance of classical logic, the quantum mind hypothesis. Classical neurobiology views the brain as a remarkably complex but ultimately classical computer, a network of neurons firing in intricate patterns to produce thoughts, memories, and awareness. But some physicists and philosophers argue this view is incomplete. They propose that the mysterious jump from brain activity to conscious experience might require something more, something that operates outside the rules of classical physics. The most famous proponent of this idea is the renowned physicist Roger Penrose. Along with anesthesiologist Stuart Hameroff, he proposed the theory of orchestrated objective reduction. They suggest that deep inside your brain cells, within structures called microtubules, quantum computations are constantly taking place. These are not simple on-off switches, but complex quantum superpositions. According to their theory, a conscious thought occurs when one of these superpositions reaches a threshold and collapses, a process Penrose calls objective reduction. This collapse is not triggered by an outside observer, but is an intrinsic feature of space-time geometry itself. The implications of this are staggering. It could provide a scientific basis for seemingly non-computable aspects of human cognition, like intuition, creativity, or even free will. It defies classical reductionism by suggesting that mind and matter are not separate, but deeply intertwined at the most fundamental quantum level. Your consciousness would not be a mere passenger in the universe, but an active participant in its very unfolding. However, this theory remains highly controversial. The main objection is the problem of decoherence. The brain is a warm, wet, and noisy place. For a quantum system to maintain its delicate superposition, it needs to be extremely isolated from its environment. Most physicists argue that any quantum coherence in the microtubules would be destroyed almost instantly by the surrounding molecular chaos, long before it could influence any neural process. It would be like trying to perform a delicate ballet in the middle of a hurricane. Yet, despite these formidable challenges, the quantum mind hypothesis persists. It forces a vital dialogue between physics, biology, and philosophy. It asks us to consider that the weirdness of the quantum world might not be confined to the realm of tiny particles in cold laboratories. It might be the very engine of our inner experience, woven into the fabric of our thoughts. And this raises a crucial question central to the entire quantum debate. If quantum systems are so fragile, how does the stable, classical world we see ever emerge from such a delicate and probabilistic foundation? The answer lies in a process that constantly washes away the quantum weirdness, a phenomenon known as decoherence. Our warm, wet, and chaotic world is the ultimate enemy of quantum weirdness. This is decoherence, the 12th great defiance of classical logic. It is the process that constantly washes away the bizarre effects of superposition and entanglement, explaining why cats appear either alive or dead, and why we never see a baseball exist in two places at once. Decoherence is the reason the quantum realm seems hidden from our everyday experience. It occurs when a fragile quantum system, like an atom in a superposition, interacts with its environment. Even a single stray photon bouncing off the atom is enough to do it. This interaction is not a deliberate measurement, but it has the same devastating effect. It entangles the quantum system with the countless particles in the environment, spreading its once coherent quantum information out into the world in an irretrievable way. The delicate phase relationships that define a superposition become randomized and unpredictable. From our perspective, the wave function appears to collapse. The superposition is destroyed, and the system snaps into a single classical state. This is the bridge between the quantum and classical worlds. It is not that quantum rules stop applying to large objects. It is that large objects are constantly interacting with their environment, making it practically impossible for them to maintain a coherent quantum state. Their quantum weirdness leaks out almost instantly. This process refines the measurement problem. It suggests that collapse may not require a conscious observer, but is an inevitable result of interaction and information leaking into the environment. The key to harnessing the power of the quantum world, for technologies like quantum computing, is to fight decoherence. We must isolate quantum bits or qubits in extreme vacuums and cool them to temperatures near absolute zero to protect their delicate superpositions from the disruptive noise of the outside world. This battle against decoherence is the central challenge of quantum information science. It shows us that the classical world we perceive is not the fundamental reality, but a stable, emergent property that arises from quantum foundations through constant interaction. If decoherence is the force that hides the quantum world from view, then what are the tools that allow us to finally see it? This pursuit has given us one of the most powerful technologies ever invented for probing reality's deepest secrets. This battle to preserve coherence against the relentless tide of decoherence is not just a scientific curiosity. It is the very foundation of an entirely new kind of technology, one that harnesses quantum weirdness itself. This brings us to the 13th great defiance of classical logic, the reality of quantum information and computing. A classical computer bit is a simple switch, a 1 or a 0, a definite state. A quantum bit or qubit is something else entirely. It can be a 1, a 0, or any probabilistic mixture of both at the same time, a superposition. This single property changes everything. With just a few hundred qubits, a quantum computer could exist in a superposition of more states than there are atoms in the known universe, allowing it to perform a staggering number of calculations simultaneously. It is not just doing one thing at a time faster. It is exploring a vast landscape of possibilities all at once. This parallel processing power is supercharged by entanglement, linking qubits together so that they share a single, correlated quantum state. An operation on one qubit can instantly influence all the others it is entangled with. This allows quantum algorithms to solve certain problems that would take a classical computer longer than the age of the universe. The most famous example is Shor's algorithm, which can factor enormous numbers into their prime components exponentially faster than any known classical method. This capability threatens the very foundation of modern cryptography, which relies on the fact that factoring large numbers is practically impossible for classical machines. Our digital security, from online banking to state secrets, could be rendered obsolete by a sufficiently powerful quantum computer. But this is not just about breaking codes. Quantum simulators could model the behavior of complex molecules, leading to revolutionary new materials and life-saving drugs. They could unravel the mysteries of high-temperature superconductivity, or map out the intricate quantum interactions that power photosynthesis. This field of quantum information science merges physics with computer science, proving a profound truth, that information is not an abstract concept. It is physical, rooted in the properties of particles and waves. The quantum world is not just a theoretical playground for physicists. It offers a new computational paradigm, one that could redefine the limits of technology and our understanding of complexity itself. And if we can harness these strange laws for computation, what does that mean for the security of our communication in a quantum age? This unbreakable security is not a promise for the distant future. It is being built today on the very principles that once baffled Einstein. Welcome to the 14th defiance of classical logic, the reality of quantum cryptography. While a quantum computer might one day shatter our current digital locks, quantum mechanics itself provides the ultimate defense, a system where secrecy is guaranteed not by complex math, but by the fundamental laws of physics. This is called quantum key distribution, and its security rests on two quantum pillars we have already explored: the uncertainty principle and entanglement. Imagine two people, traditionally called Alice and Bob, want to share a secret message. To do this, they need a key, a random string of numbers to encrypt and decrypt their data. The problem has always been, how do you send this key without someone eavesdropping and stealing it? Classically, you cannot be sure, but quantum mechanics offers a perfect solution. Alice can send the key using individual photons, each polarized in a specific way to represent a 1 or a 0. Here is where the magic happens. Because of the uncertainty principle, an eavesdropper, called Eve, cannot measure these photons without disturbing them. If Eve tries to intercept a photon to read its state, her very act of measurement forces it to choose a definite polarization, irrevocably altering its original state. When Bob receives the photon and measures it, his result will not match what Alice sent, revealing Eve's presence. It is like trying to listen to a whisper in a quiet room. Your very breathing gives you away. The most famous protocol, called BB84, uses this principle. Alice sends photons using two different, random sets of polarization filters. Bob then measures them with his own randomly chosen set of filters. Only afterward do they communicate publicly, over a regular channel, to compare which filter sets they used. They discard all the bits where their filters did not match, and the remaining bits form their perfectly secure, random key. Any attempt by Eve to spy creates errors in this key that Alice and Bob can easily detect. An even more secure method uses entangled particles. Alice and Bob each receive one particle from an entangled pair. Because their properties are linked instantaneously, any attempt to measure one particle breaks the entanglement, alerting the users that their key has been compromised. This is not just theory. Quantum encryption systems are already operating in banks and government agencies, with satellites in orbit testing global quantum networks. It is a profound turn of events that the same spooky action at a distance that so troubled physicists is now our best hope for perfect privacy. Quantum cryptography defies the classical notion that information can be copied and intercepted without a trace. In the quantum world, looking always leaves a mark. This flawless security depends on the unique behavior of quantum particles, but to understand that fully, we must ask a deeper question. How do entire groups of these particles behave when they are collected together? Their rules of social conduct are nothing like anything in our classical world. This collective behavior of particles introduces a statistical reality that is utterly alien to our own. This is the 15th great defiance of classical logic, the strange rules of quantum statistics. In our world, if you toss two identical coins, you can still tell them apart, at least in principle. One might have a tiny scratch, or you could watch their paths through the air. They are independent, distinguishable objects. But in the quantum realm, this concept of individuality completely vanishes. Two electrons are not just similar, They are fundamentally identical in a way that is impossible in classical physics. This loss of identity forces a radical rewrite of the rules of statistics, and it splits the quantum world into two distinct tribes. The first tribe consists of fermions, particles like electrons, protons, and neutrons that make up matter. They are fiercely antisocial, governed by the Pauli exclusion principle. This rule states that no two identical fermions can ever occupy the same quantum state at the same time. It is the ultimate quantum rule of personal space. Think of it like a subway car where every seat can only hold one person. This single principle is the reason atoms have structure and chemistry exists. Without it, all the electrons in an atom would collapse into the lowest energy level. There would be no variety, no electron shells, no chemical bonds, and no complex matter. The universe would be a featureless soup. The other tribe is the bosons, particles like photons that carry forces. They are the ultimate social butterflies. Not only can they occupy the same state, they desperately want to. They are drawn together, and this bunching effect leads to some of the most spectacular phenomena in physics. When a gas of bosons is cooled to near absolute zero, a magical transition occurs. A significant fraction of them suddenly drop into the very lowest energy state, merging into a single, giant quantum wave. This is a Bose-Einstein condensate, a new form of matter where millions of atoms lose their individuality and behave as one single superatom. This collective behavior is also the engine behind superconductivity and superfluidity, where electrical current or liquid flows forever without any resistance. How can this be? The root of this bizarre social divide lies in the symmetry of the particle's wave function. The wave function for a pair of fermions is antisymmetric, meaning it flips its sign if you swap the two particles. If you try to put them in the same state, the math forces the entire wave function to equal zero, making that configuration impossible. For bosons, the wave function is symmetric. It stays the same when particles are swapped, encouraging them to congregate. This reveals a profound truth, that quantum particles are not independent billiard balls. They are inextricably linked parts of a whole, their fates determined by a collective description that erases any notion of which is which. This challenges our deepest assumptions about individuality and independence, suggesting that at the most fundamental level, everything is connected by an invisible, statistical law. If the identity of particles is an illusion, and their behavior is governed by such rigid, timeless rules, what does that say about the flow of time itself? Does the quantum world even care if time runs forward or backward? The apparent irreversibility of a quantum measurement stands in stark opposition to the pristine symmetry of its underlying mathematics. This is the 16th great defiance of classical logic, the problem of time symmetry in quantum mechanics. At its heart, the Schrödinger equation, which governs how quantum states evolve, is perfectly time-symmetric. You could theoretically run the film of a particle's quantum evolution backward, and it would obey the same physical laws. There is no inherent arrow of time written into these fundamental equations. Yet, our experience of reality is dominated by one irreversible event, the collapse of the wave function. When you open the box and see the cat, that event cannot be undone. You cannot unsee the result. That single moment where possibility crystallizes into a single fact seems to break the time symmetry of the quantum world. It creates a before and an after, a past that is fixed and a future that is open. This introduces a profound puzzle. Is this arrow of time fundamental, or is it somehow an illusion? The many worlds interpretation attempts to restore symmetry by suggesting that the wave function never actually collapses. From its perspective, every possible outcome always happens, and the entire multiverse remains time-symmetric. But for you, the observer, you only experience one branch, one timeline that feels irrevocably forward-moving. This connects directly to the classical arrow of time we know from thermodynamics, the tendency of the universe to move from order to disorder. Perhaps the quantum measurement process, happening countless times everywhere, is the microscopic engine that drives the increase of entropy and gives time its direction. Some physicists even speculate that the very first quantum fluctuation, the initial moment of the Big Bang, might have set the entire cosmic clock ticking forward. This forces us to reconsider time itself. It may not be a fundamental stage upon which the universe plays out, but an emergent property that arises from the countless quantum interactions happening all around us. We are left wondering if the flow of time is simply the feeling of the wave function collapsing over and over again. And if particles and their behaviors are not the full story, what are the deeper, more fundamental entities that give rise to them? But what if the particles themselves are not the fundamental story? The 17th great defiance of classical logic asks us to erase the tiny billiard balls from our minds entirely and replace them with something far more profound and strange. Quantum field theory presents a universe not of isolated objects, but of vibrant, dynamic fields that fill all of space and time. Think of the entire cosmos as an immense, invisible ocean. This ocean is not made of water, but of various quantum fields, one for each type of particle. An electron is not a tiny dot. It is a localized ripple, a tiny wave of excitation in the everywhere present electron field. A photon is a vibration in the electromagnetic field. Even the Higgs boson is a splash in the Higgs field. In this view, particles are not primary. They are merely the quantized manifestations, the smallest possible packets of energy that these underlying fields can produce. This framework is the bedrock of all modern particle physics, seamlessly incorporating Einstein's special relativity and explaining how particles interact. Forces are not magical pulls. They are the result of other particles being exchanged. The electromagnetic force, for instance, arises from electrons tossing virtual photons back and forth between them, like players in a subatomic game of catch. This is how quantum field theory describes every interaction in nature. It also gives us the Higgs mechanism. The Higgs field is like a strange, invisible molasses that fills the universe. As particles move through it, they interact with this field, and that interaction is what gives them mass. A particle that interacts strongly, like a top quark, becomes very heavy. A particle that interacts weakly, like a photon, remains massless. This completely shatters the classical notion of mass as an intrinsic, solid property of an object. Mass becomes a dynamic consequence of a particle's relationship with an all-pervading field. The success of quantum field theory is staggering. Its predictions have been verified with breathtaking precision, down to the 12th decimal place. It forces us to accept that the solid, particle-based world we perceive is an illusion. At its heart, reality is a set of interacting, probabilistic fields. Matter and energy are not just interchangeable, as Einstein showed. They are simply different expressions of the same underlying, vibrating reality. This framework extends the quantum weirdness of probability and uncertainty to literally all scales, suggesting that fields, not things, are the true foundation of everything. So what does this immense success truly mean? It hints that we may be edging closer to a theory of everything, a single, elegant description that unites all forces and all particles under one grand, vibrational roof. The mathematics of quantum mechanics works flawlessly, but its meaning remains one of the greatest unsolved puzzles in science. This is the 18th defiance of classical logic, the bewildering array of interpretations that attempt to explain what the equations actually mean. Each interpretation accepts the same, undeniable experimental results, but then tells a completely different story about the nature of reality behind those results. It is as if we all agree on the plot of a movie, but cannot agree on whether we are watching a drama, a comedy, or a horror film. The most famous is the Copenhagen interpretation, which essentially tells us to stop asking what is happening before we look. It posits that the wave function collapse is a fundamental, random process, and that reality is not objective until it is measured. This was the pragmatic view adopted by most of the founders of quantum theory, but it leaves a glaring question unanswered. What or who qualifies as an observer capable of causing this collapse? Is it a conscious mind, or simply any interaction with the environment? In stark opposition stands the many worlds interpretation. It takes the equations at face value and declares that the wave function never collapses. Instead, every time a quantum event has multiple possible outcomes, the entire universe splits into branches. In one world, you see the cat alive. In another, an identical version of you sees it dead. There is no randomness, only a deterministic unfolding of every possibility across an infinite, ever-branching multiverse. This interpretation avoids the mysterious collapse, but at the incredible cost of believing in an uncountable infinity of parallel realities, all equally real, yet forever beyond our reach. Then there are attempts to return to a more classical, intuitive world. Pilot wave theory, for example, restores determinism by proposing that particles are real, point-like objects guided by a hidden wave. This seems comforting until you realize the theory must be profoundly non-local. The guiding wave instantly influences the particle regardless of distance, embracing the spooky action at a distance that Einstein hated. These competing visions show us that quantum mechanics is more than just math. It forces us to make a philosophical choice about the nature of reality itself. Do we live in a world that is fundamentally random, infinitely branching, or secretly deterministic but connected in impossible ways? Each interpretation defies classical logic in a different manner, and there is no experiment yet to tell us which one is correct. They are all valid stories that fit the data. This suggests a profound possibility that reality might not have a single true nature. It might be relational, defined not by absolute properties but by the connections and interactions between things. The world you experience could depend on the questions you ask of it. This relational view of reality finds its ultimate expression in a principle so deep, it challenges the very idea of a fixed, knowable world. This is quantum contextuality, the 19th great defiance of classical logic. It reveals that a quantum particle does not possess properties in isolation. Its attributes, like spin or position, do not have a definite value waiting to be discovered. Instead, their value is born in the moment of measurement, and it depends entirely on the specific context of the experiment, on what question you choose to ask. Imagine asking a single electron, "What is your spin along the vertical axis?" The electron will give you a clear answer, up or down. Now, if you immediately ask it again, you will get the same answer. It seems to have a definite property, but now change the context. Ask it first about its vertical spin, and then ask about its horizontal spin. The answers will be random, and crucially, the act of asking the second question completely erases the definite answer you got for the first. The electron's property was not pre-existing. It was defined by the specific conversation you had with it, by the full set of questions you decided to pose. This is not a limitation of our tools. It is a fundamental feature of the universe. The physicist Carlo Rovelli built upon this with his theory of relational quantum mechanics. He proposes that there is no absolute, God's-eye view of reality. States and properties are not inherent to an object. They only exist in relation to another system that is interacting with it. For you, the observer, the electron has a definite spin. But for another particle that has not interacted with it, that electron remains in a fuzzy superposition of all possible spins. Both perspectives are equally valid. There is no single, true state of the electron independent of any relation. This dissolves paradoxes like Wigner's friend, where one observer sees a definite result inside a lab while another outside still describes the entire lab as being in a superposition. In a relational world, both descriptions are correct relative to their own interactions. This is a monumental shift from the classical world. We are not passive discoverers of an objective external reality. We are active participants in a cosmic dance of relations, where properties emerge from the connections we make. It suggests the universe is not a collection of things, but a web of relationships. If reality is truly this fluid, defined by interaction and context, then what is the final, most profound implication for our understanding of existence itself? This final, breathtaking defiance forces us to abandon the very last shred of a classical world-view. Quantum contextuality proves that nothing in the quantum realm possesses inherent, independent properties. The outcome of any measurement you make does not reveal a pre-existing fact. Instead, it is created in that very moment, and it depends entirely on the full context of your inquiry, on what other questions you choose to ask at the same time. It is as if you asked a friend how they are feeling, and their answer changed based on whether you also asked about the weather or their job. Their mood would not be a fixed internal state, but something that emerges from the entire conversation. This was mathematically proven by the Cauchy-Specker theorem, which shows it is logically impossible for a quantum system to have predetermined values for all its possible observable properties. The universe simply refuses to be pinned down in that way. This makes reality profoundly participatory and relational. An electron does not have a definite spin. It has a potential to give you a spin value, but that value is only defined in relation to the specific axis you choose to measure, and in the context of the other measurements you are performing. This interdependence means the whole experimental arrangement matters, not just the isolated particle. It is the final nail in the coffin for a universe of separate, independent objects. Quantum mechanics is not just a theory of tiny things. It is a radical statement that the world is a web of connections, where properties are not owned but are granted through interaction. This contextual nature is not a bug. It is a feature, one that is now being harnessed in the development of advanced quantum technologies, where computational power relies on this very interdependence. So, after journeying through these 20 astonishing ways, the quantum world defies all logic. From cats that are both dead and alive to particles that whisper across the galaxy. What does it all truly mean for our understanding of reality itself? The universe revealed by quantum mechanics is not a collection of separate, solid objects, but a deeply interconnected and dynamic web of potential. This journey through 20 astonishing paradoxes shows us that the classical logic governing our daily lives is merely a useful approximation, a simplified interface for navigating a reality that is far stranger and more fluid at its core. We are forced to abandon the comforting ideas of absolute objectivity, of a universe that exists in a single, definite state independent of us. Instead, we find a participatory cosmos where the act of observation is woven into the fabric of existence, where properties are not inherent but relational, and where spooky connections defy the very notion of empty space. This fundamental revision of reality has profound implications. Philosophically, it challenges reductionism, the idea that we can understand the whole by breaking it down into its independent parts. Quantum mechanics suggests the whole is primary, and the parts derive their meaning from their connections to everything else. It forces us to reconsider the nature of consciousness and our role as observers. Are we merely witnessing the universe, or are we participants in its ongoing creation? Technologically, this quantum weirdness is no longer just a theoretical curiosity. It is the engine behind a second quantum revolution, powering the development of computers that can solve problems intractable for classical machines, and cryptographic systems where secrecy is guaranteed by the laws of physics themselves. Embracing this quantum view does not make our classical world any less real, but it does expand our understanding of what reality can be. It is a call for humility and boundless curiosity, a reminder that the universe has layers of mystery that our everyday intuition cannot grasp. The greatest lesson may be that the answers to our deepest questions about existence will not be found by forcing the cosmos to fit our logic, but by having the courage to adopt a new logic that fits the cosmos. So where does this leave us, standing at the edge of this vast and puzzling quantum frontier, armed with wonder and a new set of rules? This new understanding of reality is not a distant abstraction, but a force actively reshaping our world. The technologies emerging from these 20 quantum defiances, from unbreakable encryption to unimaginably powerful computers, are proof that the universe's deepest mysteries hold the keys to our future. They show us that the bizarre rules governing particles are not just curiosities for physicists, but the fundamental operating system of existence itself, waiting to be harnessed. This journey through superposition, entanglement, and the blurry line between observer and observed leaves us with a humbling yet exhilarating truth: that the cosmos is far stranger and more wonderful than our classical senses could ever perceive. As the great physicist Richard Feynman once noted, if you think you understand quantum mechanics, you probably do not understand it at all. And that is not a failure, but an invitation. An invitation to remain curious, to question everything, and to continually marvel at the profound wonders hidden within the fabric of the universe. We hope this exploration sparked your sense of awe. If it did, please like this video, share it with a fellow curious mind, and subscribe for more journeys into the heart of space and science. Let us know in the comments which quantum defiance amazed you the most. Thank you for watching, and never stop questioning the nature of reality.